All right, so we continue free body diagram of rigid body, rigid bodies. But the problems I've chosen today are kind of a review of last section of chapter 4. Equivalent system and distributed load as well. So it's two birds with one stone. So we're gonna do that. So let's start with number 12. All right, let's look at this one. Show the distributed loading on this beam as a single equivalent force and finds its location from point A. Part B, find supports reaction. All right, let me take this onto the whiteboard right away. So that should be good. All right, so the first goal is to replace this loading, which is a distributed loading on this bridge or beam, by just one single force. I'm not doing the distributed loading yet. I'm not doing free body diagram and stuff yet. I just want to find the equivalent system, meaning I want to find something like this with just one force, Fr, and its location, let's call that X bar at point A. So again, tell me what is Fr in words. I'm not looking for numbers yet.
The area under loading.
So it's area under loading. Remember that. That's all you got to remember from distributed load. The equivalent force is area under loading. And what is the distance that we are trying to find? What is the X bar?
Your centroid.
Centroid of the area. Perfect. The center of that area, right? This area is a little bit weird, right? For me, it's difficult to find the centroid of it. So what I'm going to be doing that we've done before, I'm going to divide it into two areas. I'm going to do one here, right? I'm going to break it into simple areas that I can find the force, and a triangle on top. Now I can.
Dr. Amir, you should shut off your video.
I should what?
So you get a little bit better connection.
Oh,
shut
sure,
off your video.
Sure. Okay. Let me also message my daughters, make sure they're off.
You kind of cut in and out, so maybe that'll help.
Yes. Okay. Also send a message to my kids and make sure they're off of stuff. They do also schoolwork at the same time, so. All right, is it better now, Colton? Is it okay?
Yeah, it's a lot better.
Okay.
Better.
All right, so we'll see. Okay, now I have two areas. So I'm going to have a rectangle here. Okay. Which is going to have an F, let's call that F1 at a distance of X1 or X bar 1. And then, yeah, I should have used proper color, and then I'm going to have a triangle. That one is going to have a force, F2, and that is going to have a distance of X bar 2. Okay, so now let's do these two. F1 is the simple one, right? Just a rectangle. It's a 2. And again, the units are extremely important here. Kilonewton per meter multiplied by 6 meters. This gets canceled with this one. I'm looking at 12 kilonewtons. Okay, units here are a way for you to help you to make sure you're doing the right thing and going the right way. All right, x bar 1 is going to be half of that distance. Center of a rectangle is going to be located on that line. 1/2 of 6 meters, so that is 3 meters. Okay, define that one. Questions so far? Okay, let's do the triangle. I'm going to do it here. F2 is area of the triangle is 1/2 of the base of triangle, which is 3 meters, by the side of it, which is 4. Is it 4?
It's
Oh,
2,
wouldn't
isn't
it
it?
be 2?
It is
Yeah.
2. Yes. So this is 2. This is 2. Yeah, see, I almost made the mistake. If you're not careful, 1 second, you can just make a mistake right there. Everything else after that is just going to snowball. 2 kilonewtons per meters. This, so we get 6, 3, so 3 kilonewton is my F2. X bar 2, what is that distance? So from point A to the centroid of this triangle.
Isn't it 5 meters?
So it is 5 meters. It is this 3 meters right here, right? It is 3. So 3 meters plus, this is a 2/3 of that length, whatever that is. 2/3 of 3 meters. Okay, so it's going to be 5 meters. Questions? Okay, so let's see. Now I have this, right? It's one step at a time. I have F1, sorry, the forces are kind of crooked, which was 12 kilonewton. And then I have another one. Remember I said force is a sliding vector? Although it's up there, I can just slide it down on its line of action and nothing will change. It's okay to move a force on its own line of action without, messing anything else. So, and then there's another 3 kilonewtons. And then let's put the distances. This one is 3 meters. And this one right here is 5 meters. This is what I have. Doesn't matter if you put the pin and support and stuff like that. Kind of doesn't matter at this point. Okay. Now the goal is, remember, this is my end goal up top here, right? To just have one force. I don't want 2 forces. So now here's what you gotta remember, the equation that we have. FR is summation of forces, right? MR is summation of all the FDs, or in 3D case, R cross Fs, plus summation of existing coupled moment, which in this case, I don't see any. I'll only see 2 forces, right? So this one is 0 here. And then the distance D that we are looking for is just MR divided by FR. So have these equation handy because this is what you're going to need in your exam if you see a problem like this. So let's do that. FR is going to be, D is the same as X bar, by the way. That's what I mean. Okay. FR is just summation of the forces. 12 kilonewtons plus 3 kilonewtons is 15. Simple enough. Some people, as I said, like to be very accurate with the signs. They put a plus here, and then so these are going to be negative and so on, which is totally fine. MR is going to be summation of FDs. So it's going to be a 12 kilonewton, they're all in the same, going the same direction. 3 meters plus 3 kilonewtons by 5 meters. You got to be very careful and carry the units throughout your calculation. So hopefully on the exam on Wednesday, this is what I want to see. See how I have units everywhere next to my numbers? So please have those throughout your calculation so you don't end up with a number that you're not sure what the unit is, so you just put a unit that you think is right next to it. This is the proper way of doing it. This will result in 36 and 15 kilonewton meters. Is that 51, right? Okay. So distance D that we are looking for is going to be 51 kilonewton meters divided by my FR, which was 15 kilonewtons. This one cancels this one. So it makes sense, right? I'm looking for a distance and it's going to give me a meters. Okay, so goal 1 achieved. I replaced that distributed loading by just one force located at a distance. Questions about how I did it? So what I have right now is like this. A force of 3.4 meters, a force of 15 kilonewton at 3.5 meters. Any questions about simplifying distributed loads, stuff like that? Okay. Part 2 said find support reactions. Okay, now we're talking equilibrium. Now we're talking free body diagram. If you guys are done, I'm gonna wipe this off just to start the part 2. Okay. So forget about the distributed load and stuff right now. I can get rid of this too. Okay. So right now what I have is a beam with pin, with roller on one side, and 51 kilonewton located at 3.4 meters. This is what I want to do. Now I got to draw a free body diagram. So nothing that I've had so far was a free body diagram because it wasn't free, right? It wasn't free of supports and stuff like that. Step 1 of free body diagram, outline of the shape. Now I cannot include the pin or the roller, stuff like that. Otherwise, I don't have a free body diagram. Step 2.
Your FR should be 15, not 51.
Oh, 15. Yes, you're right. Thank you. Thank you. Step 2 is to put active forces. The only active force I see is that 15. Okay. Step 3 is to put reactive forces, the forces that are trying to support this beam. Now I would like to make that little table here. I have pin A and I have roller B. X, Y, and moment. All right, let's look. Pin A, I hope everyone knows by this point how the supports work, right? Every way that they do not move, that's when we're going to put a force. So does this move in X or Y direction? Only the pin.
No.
No. So both of them are no. Can this beam rotate about point A if it wants to?
Yes.
Yes. So that's a yes. All right. So and I have to put two forces. I, again, usually like to put them in the positive direction, but if you want to put them opposite way, that's totally fine. All right. Point B. Does roller at point B can it move in X direction?
Yes.
If it wants to, yes. Can it move in Y direction? Up
No.
or down? It might
No.
go up, right? Yes, but it won't go down. So I put a no there. And it's just sitting on that roller, so it can rotate about point B if it wants to. So the only N that I'm going to put on there, the only force is going to be my BY. So this is the free body diagram for this beam. All right, I have three unknowns. I should be able to do it by just three equations, sorry. Let's see, summation of forces in X direction being 0. Anything that goes to the right, I'm gonna take positive. I usually like to start from one side of the beam and kind of move. Let's see.
AX is the only one in there.
AX is the only one. So AX, I don't see anything else, so that should be 0. You don't need to go back and erase it or cross it or anything. This is your correct free body diagram. But this problem, because there's no horizontal force anywhere, so pin A doesn't even have to generate that axial force. Okay. Summation of forces, I want to say Y, but then I have two unknowns. Let's do a moment about point A or B. Doesn't matter. Summation of moments, and let's take anything that rotates this way to be positive. Okay. I start from the same point A. AX, AY, they both go through point A. I don't have to worry about them. I have a 15 kilonewton multiplied by this distance, which is 3.4 meters. And this, is it positive or negative? You got to look at my sign and look at which way this is going. Is this trying to rotate the beam in the
Negative.
Negative, because it's rotating clockwise.
clockwise? So if I pin it here, this force is trying to push it down, so it's going to start rotate this way. It's this way clockwise. I check it with my sign. They're opposite of each other, so minus. Keep moving. I get BY, and the distance between BY and point A is 6 meters. Let's figure this out. Beam BY is pushing it up. If it's pinned at this point, it's going to rotate this way. It's going to rotate this way. I check it with my sign. That's a plus. So should be good. If you do this one, you're going to get a BY of, let me see, BY of 8.5. So BY is 8.5 kilonewtons. Last equation I have is summation of forces in Y also needs to be 0. Okay, so I start from one side. Everything that's either pointing up or down. I have an AY, which is going up. Keep moving. I have a 15 that's pointing down. And keep moving. I have a BY that just found out to be 8.5 kilonewton pointing up. All of these needs to be 0. And this will give me AY of 6.5 kilonewton. Okay. Questions? So if you want to practice, so practice this problem, but this time from one step further back before we had one full force in here. Remember, there was a step that we had the two forces on there. One was 12, and then there was one was 3. So one step before this. So try to do, just as a practice a little bit, try to do this one and see if you get the same answers. Because remember, I keep telling you, these are all equivalent, means they are the same thing. We just move the forces around. This was 3, this was 5. So just do this on your own time as just to have a practice and see if you get the same AX. Well, AX is the same, you can already see. But let's see if you get the same AY and BY, and if that makes sense. All right. Okay, let's look at another one. Similar, so we're gonna move a little bit faster, but just more practice here. Number 16. Okay, this has been exam problem a couple of times. So show the distributed loading on this beam as a single equivalent force and find its location from point A. Again, replace everything that you see here and put just one force. Find reactions at point A and B necessary to keep the beam in equilibrium given the loading shown. All right. So let's see. The first thing I do is I kind of got rid of that distributed load. You know what? Let's bring this one to the whiteboard too. There. All right. Okay. So the first thing I do is get rid of that distributed load and replace it by a force FR, or I shouldn't say FR, let's say F1 at X bar 1. So you guys are kind of quick by now. F1 is area under loading, is 40 kilonewtons per meter. Again, it's important to include the units to make sure you're not making any mistakes. Okay. And location of it is going to be half of 8 meters from point A, so it's 4 meters. There we go. So what I have, I transfer that into this, transferred it into 320, 20, this moment, and B and A. So one step at a time, right? This is what I've done so far. The problem again wants me one force. So the problem is looking for this. FR at D or X bar. This is what the problem is trying to do or asking me to do. So I got to go back to your equation. So I want everyone to look back at the equation that we just had. The governing equation or the main equations that we have to find FR and D. So what is it? What is FR?
You solve it like a rectangle, so it's your length times your width. So your down force was what, 40 kilonewtons times your distance, 8 meters.
No. I'm just looking for FR.
The sum of all the forces.
Sum of all the forces. Okay, I think you were talking about this step, which
Yeah,
we
that was
already
my
did.
bad.
Yes, yeah, we already did that. What about, so let's do this one. Summation of all forces. I see at 320 kilonewtons, and you know what? let me use the signs this time. Anything that points up is going to be plus. So this is a minus 320, minus 20, and that's the only two I see, minus 340. Okay, so I found this FR, minus 340. Well, I shouldn't say minus. Well, it doesn't matter. You guys know that minus is the direction at this point. Okay. What about MR? What is the equation for MR? Just look back at your notes for the problem that I just did before this one.
It would be the moments of those two forces and also any existing moment.
Exactly. So it's going to be summation of FDs, right? Plus summation of existing. All right. Let's use the sign for this one too. Anything that goes counterclockwise, I'm going to take positive. All right. So summation of FD. So it's going to be 320 multiplied by the distance was 4 meters. And this is going this way against my sign. So it's going to be negative. Moving on, I get to that 20. So 20 kilonewtons multiplied by the distance. So it's 8 meters plus 3 meters. That one is also rotating this way. So that one is also negative. Okay. And then 150. And that one is also showing that its rotation is this way. So that one is also negative. Okay. When this I think has been exam problem twice. Every time I saw a lot of students, they forgot this moment. They keep forgetting this existing couple moment, right? Let me ask you this. What caused that couple moment to be on the beam?
Does your F of R cause that?
Wouldn't it just be an existing couple of forces that just got simplified to that?
Exactly. So the answer is the same thing that I can ask you this question about this 20 kilonewton. I say, hey, what caused that 20 kilonewton? You know, we don't know exactly, but it's a force there. It's existing. Nothing that you guys did or FR that we found causing this moment. This is an existing. So there were some forces somewhere, I don't know, a couple of forces, or maybe there is a person in, applying that couple's moment there. But these are existing. Same as this distributed load, existing. I don't know where they come from. The answer, that's a little bit of a trick question when I ask where does it come from. The answer is I don't know. And someone actually said it very well. It said two forces that were simplified to a couple. Exactly. There were two forces. I don't know how much, but the resulting moment was 150. And that's how it turns out to be. These are existing. Okay. The last thing I got to do is find my distance, which is going to be MR over FR. You can include the sign. You don't have to, because we consider the sign for both of them. Kilonewtons. We can totally do that. Your D distance is going to be 485 meters. So 485, and your FR is 340. So remember, these are the important equations that you need. Oh, sorry. Got to go here. And your D. Then you are simplifying a system. Okay. In 3D problems, it doesn't ask for a distance usually. It just says simplify to a force and a moment, because in 3D it really doesn't make sense to find one force at a distance. So for 3D, you have the exact same equations. The only difference is there's an arrow on top of these, and this FR is R cross F. So your MR is just going to be summation of R cross Fs. Summation of existing couple moment. So that's the only difference. Okay. Questions about distributed load, simplifying, any of that? Okay. So let's get back to a 3D problem. Let's do problem number 10. This is 16, so 10 is going to be right here. Okay. This also has been an exam problem. The bar AB has a fixed support at A. Okay. Yes, I see it. The collar at B is fixed to the bar. The tension in the rope BC is 300 pounds. Draw the free body diagram of the bar. Find the reaction at point A. And then if support A can sustain this much torque, okay, well, maybe you should have not said torque, just said moment. Can it cause failure? Show all your work. That was a bonus point, 2 points, blah, blah. Okay, so simple thing is there's a tension of 300 in this rope, and it says find the reaction that point A is creating because there's a tension there. So let me see. Let's get this one transferred over. All right. So step 1 is to draw a free body diagram. It says there's a tension. It's a tension, so it's going away from point B on this rope, 300 pounds. Okay. Step 1 is to draw a free body diagram of your rigid body. The of is very important because that will tell you what you need to isolate and what you need to draw the outline of. What would you draw the free body diagram of here?
AB.
Just AB, right? So I'm going to draw a free body diagram of pipe AB. So when I do step 1, which is isolate this, I'm just going to draw the pipe AB. That's it. You know, realizing what you're drawing the free body diagram is preventing you from having too many unknowns, because if you don't do that, I've seen it a lot. The students include the rope and then there is a force here and it just gets complicated. Okay. All right. Step 1 was isolate. Step 2 is active forces. The active force, the only active force that's given to me is that T of 300. Okay. What about step 3 is reactive forces. This is a fixed support. So what does that mean when I say something is fixed? Does it move?
It can't move about point A.
It can't move, right? It's fixed. Can it rotate about point A?
No.
No, it's fixed. Okay. So fixed support, if you want to draw X, Y, Z, MX, MY, MZ. You guys already answered that. Does it move in X? No. Does it move in Y? No. Does it move in Z? No. Does it move in rotate around MX? No. MY? No. MZ? No. So it has 6 unknowns because it's 100% fixed. No rotation, no translation. So I'm going to put an AZ, AX, AY. I'm going to put an MZ, mx, my. Let's put the rotation on them too, so when we look at them, we are clear that hey, these are moments. Although we said m, but okay. 3 unknowns. I got to use all my powers, right? All of the six equations that I have. Summation of forces in vector form equals 0. Summation of all moments vector form equals 0. Okay. Let's just start with forces. Forces are easier always. What do I need before I can actually write this equation? AX is in X direction, AZ in Z direction, AY is in Y direction. So what else? What other force do you see here that needs a little bit of work?
Needs to be broken down into its X, Y, and Z components.
Exactly. So the tension, I need a vector for my tension. It is not a vector. This is a magnitude, right? We're going back way to chapter 4 when you had a magnitude. You want to transfer it into a vector, or in this case, a t, right? So what you do is you put that magnitude, you do a unit vector next to it. In this case, what unit vectors should I use?
BC.
BC, exactly. Unit vector of BC. So I put this magnitude next to unit vector of BC. All right, unit vector of BC, going back to chapter 2, it's going to be RBC divided by magnitude of RBC. It's going to be, I'm going to do it a little bit faster, 2I minus 6J plus 1K divided by the magnitude of that is going to be 2, 6, 1, right? And this is going to be 6.4. That's meters, or that's feet, and feet. There we go. So my T is going to be 300 pounds, and that unit vector, 2I, 6J, 1K, divided by 6.4. Meters doesn't have any units. All right. I have done the math on it if you want to have the final answer. 93.7 I, 28.1 J, 46.8 K. The units are pounds. Now I think I have everything I need to just at least do the forces, right? Point A, if you want to just write it like a vector, you can. Force A is going to be AXI, AYJ, AZK, something like this. If you want to, you don't have to. All right, let's look at it then. Summation of forces in X direction is 0. All the I's you got to add together. AX, so it's going to be AX plus 93.7 equals 0. I forgot the units, pounds. Okay. Summation of forces in Y equals 0, means all the J's. I have AY and I do have this. So AY minus 28.1. You know what? Let's write it this way. So when you guys review it, you remember. Pounds equals 0. And lastly, summation of forces in Z direction equals 0. AZ plus 46.8 pounds equals 0. Easy enough, right? So my AX is going to be minus 93.7. AY is going to be 28.8. AZ is going to be 46.8 pounds, pounds, and pounds. Okay, is there a question?
Yeah, Ryan asked
Okay, let me check the
something.
question here. Where's the chat?
How is 93%?
Okay. How is the but shouldn't be smaller than J based on the unit vector? $28.93. You're right. It's 281. Sorry, not 28.1. Very, very good observation. So here's the thing. The unit vector is 6.4, right? Minus 6 over 6.4 minus 1 over 6.4, right? They're all multiplied by the same number. Shouldn't this be, yeah, so how is this one smaller than that one? That doesn't make sense, right? So this is a bigger number. So that's how Ryan actually figured it out. Appreciate it, thank you. It's a really good sign that people pay attention. 281, yes. 281, thank you. Everything should make sense, right? Okay. Questions about F before we do the moment next? So I had forces F or A. Oops.
Also, AZ should be negative.
AZ should be negative too. Yes, thank you. This, yes, this is positive, that's negative. AX, A or F. Okay. I can write the same thing for moments. Remember, look, moments, the unknown moment at point A, I have MXI, MYJ, MZK. Okay. I just put these three together. Same as A when I put AX, AY, AZ together, just for my own clarification, and I have a better tracking of them. Okay. So all you have to do is write summation of moments in vector form equals 0. Okay. Summation of moments, for example, about point A equals 0. I have 3 moments already here. MXI plus MYJ plus MZK. What else do I have? What else creates moment about point A?
Your tension.
My tension, right? The tension, what is the moment of this tension about point A?
R cross F.
R cross F, right? So it's going to be R cross my T. If you had any other forces, it would just be another R cross T and so on. Questions about this? These are unknowns. Remember, these are the one I want to find unknowns. R cross T, the R is going to be, remember, from the point to line of action of the force. So my R can be either AB or AC. They're both acceptable. Both of them are acceptable. It needs to start from the point, but it needs to end on the line of action of force, which is both B is on the line of action, C is on the line of action. This is line of action. So it's going to be MXI, MYJ, MZK plus I, J, K, R. I think I picked A, B. So it's going to be 6, 6, 2. Because A is at 0, 0, 0. And my T, which already I found it, 97, 93.7, 281 minus, no, 46.8. Okay, so if you do the math, it's going to be mx I, my j, mz k plus 843 pound-foot I minus 93.7 pound-foot j. This is the result of this determinant. Plus 225 pound-foot k equals 0. This whole thing should be 0. So all you have to do is just this plus this should be 0. So mx is going to be minus 843 pound-foot. This and my needs to be 0. So my is plus 93.7 pound-foot. The magnitudes are similar to the one that we found before, right? The 80, well, never mind. The other magnitude was for AX, so totally irrelevant. And finally, your MZ is going to be 2250. Sorry, this one was negative. This should be minus. Okay. 2250 pound-foot. The problem also said point A can only uphold 3,000 pound-foot. Do you think point A will fail or not? And how would you determine that? What is the moment at point A? Let me ask you that.
It's just the magnitude of all the moments about the axis.
Exactly, it's the magnitude, right? So because this is a moment, don't let it trick you. It's no different than a force, right? If you had a force of 100I, 200J, 300K newtons or pound, your magnitude of force was 100, 200, 300, right? The magnitude. So same thing, you cannot compare it with individual components, but you have to find the magnitude of your moment, which is going to be 843, 93.7, 2250 pound-foot. It's going to be 2405 pound-foot. So does it fail or no?
No.
It doesn't, right? So all you have to do is just compare this. It can hold up to this much. It hasn't reached that value yet. It's kind of close. You know, I wouldn't put more forces than that on that rope, but the answer is no, it doesn't fail because your magnitude is not there. Okay, questions?
Is the reason that there are no reaction supports at B because it's fixed to the bar and it's just getting pulled from there?
Yes. Yeah, so the force at B is just that tension. You know, it's not supporting anything. It's just a tension that's put on the point B. Yes. So it's no different than when you have a beam and end of it is attached with a rope is holding it up there. All it is, it's not a, it is a support, but the only thing that there is just the force that goes up. Okay. All right, so no lecture on Friday. Remember that. It's my gift to you guys. The only thing I want to mention is I uploaded the next activity that is due after Thanksgiving, not Thanksgiving, spring break. So read activity 5, no, wait, I uploaded wrong document. So I have to go back and upload it. Yeah, I just updated it this morning, but anyway, yeah, I think I totally did it. But also I will add all of the example videos of chapter 4 and chapter 5 right here by the end of the day. I swear I updated the document. I probably uploaded the older version. But anyways, all my examples for chapter 4 and 5 are going to be available to you by end of today. So you can watch my video, the same problems that I did in class. I'll upload the lecture video of today, and I will add the activity 6 on here. There is an example for activity 6 that you can watch on the look at it. It's from previous semesters. So this is what you guys are going to be doing. You're just going to make your own static problem. A lot of students go with like books on bookshelf because it's you know, distributed load. It's really good. So, but you can go through them and see some examples. You're not supposed to copy any of them, but that's your next activity, to make your own static problem around your house and around your dorm room. Okay. Sorry, I went way over 2 minutes. Any questions or comments? I'll be online. Yes, someone said, can you pull up the, there we go. Otherwise, you guys are good to go. Okay.